Okay, continuing to work through our playlist on limits. We have here today a really important topic related to limits, and that's continuity. So we have here on the board 4 different graphs, and probably just from like an intuitive sense of what continuous means, you may already be able to guess which of these is continuous and which of these are discontinuous. I actually quickly Googled the word continuous just to see like the exact definition, and it had things like unbroken or without interruption. And that kind of looks like our first graph, right? There's no breaks in it. It's just a smooth curve. So this first graph here, this is what we would call continuous. And hopefully I can spell continuous. But these other 3 graphs we'd call discontinuous. They all have breaks in them of some kind. Even though the break could be at just one point like this, we still call these 3 other graphs discontinuous because of these breaks. So at this point, we're not being very precise. We're just kind of getting a feel for like what a continuous function looks like and what discontinuous looks like. And still just getting a feel for it, what we can say is a continuous function we can draw without lifting our pen. So just notice, this is like kind of like an x cubed curve. Well, I can just draw this, right? I can't draw it well, but I can draw it just by keeping my pen on the board. But something like this, there's no way I can draw this by keeping my pen on the board. I have to get up and do this. The same thing here, what I can do is I can kind of go here, but in order to draw this other point, I have to lift my pen. Now here, I was thinking someone, if they were really sneaky, what they could do is they could keep their pen on the board. They could keep their pen all the way around this circle and then keep going. And then they could say it's continuous. But actually, it doesn't really work that way. That's actually cheating. Because what's really going on here is it's not defined at this point. So like in reality, there's nothing there. So when you draw it and you try to not remove your pen, you're really stuck right here. You got nowhere to go. In order to go from here to here, you have to lift your pen. So you can't just draw this thing. That's not. And this one here is actually called a jump continuity, where like the graph just kind of jumps to like a different place. But these 2 here are called removable discontinuities. Kind of intuitive, as it's like someone just removed it at one single point. Next, we just have here in blue our definition for continuity, which is pretty straightforward, right? We're saying that the limit as x approaches a of f of x is just the same thing as plugging in a. So just to clarify on this, what this means, we have our function here, we'll call this our f of x, and let's say we have some point a. Well, we know how to get f of a. F of a is just our point on the curve. So plugging in a, let's say we find our f of a is 3. This is just telling us for a continuous curve, our limit at a is going to be just f of a, or 3 in this case. And then just from this definition, there's all these other kind of conclusions that we can pull out of it. This is just something to be aware of, but it doesn't really add anything to the definition, because just based on this, of course f of a exists, and of course the limit has to exist in order for us to find it this way. And then also, just based on our definition of the limit, if the limit as x approaches a is f of a, well then the right-handed and left-handed limit also have to be f of a. So next, let's just look at a more detailed example of how this is going to work. Okay, now we have our graph over here to the left, and all we want to do is we just want to check the continuity at these 4 points, and we'll start with the first one. So we want to look at -1. Now you clearly can see the graph is discontinuous based on what we said before, that there's all kinds of breaks in it. So starting with -1, we want to look at like f of a. So our f of a value, we'll check this first, our f of -1, well, we can see the value at -1 is undefined. So in this case, we actually don't have an f of a value, so we're undefined here. This doesn't exist at -1. So really what our limit is doesn't matter. It looks like our limit as x approaches -1 here is going to be about 2, just kind of like eyeballing it. That looks like about 2. We're not being too precise. We're just going to use the graph and say this limit seems to be around 2. But 2 is not equal to undefined. So at this point, -1, we're going to just say this is discontinuous. Okay, continuing on, looking at the point at x equals 1. So we'll look at our f of a value. So f of 1, for our f of 1 value, it looks like it's going to be this point up here, but it's got this removable discontinuity. So we're going to say our f of 1 is equal to 5. And then for our limit as x approaches 1, so just kind of eyeballing the limit at x equals 1 on the left and right, this looks like it's about 3. So we'll say this value is 3, but 3 is not equal to 5. So at this point, so at x equals 1, we're going to say again, this is going to be discontinuous. Okay, so moving on to x equals 3. So looking at f of 3, that's going to be just 0, looking at the graph here. And then let's just look at our limit as x approaches 3 of f of x. From the right side, looking at 3 plus, that's going to be about 0. But from the left side, trying to get the limit, it's going to be about, I don't know, let's say 4 or something, 4.5, let's say. But 4.5 is definitely not 0. So this limit does not exist. And kind of going back to our implications from the previous board, if the limit doesn't exist, then you can't have continuity. So again, we're discontinuous at this point at x equals 3. Okay, and then last one, we'll just look at this at x equals 4. So for our f of a value, f of 4, this looks like it's about at minus 3. And then we'll just take our limit as x approaches 4 of our f of x, and we just again eyeball it. But there's nothing really special going on here from the left or right. So we can just say our limit looks like it's minus 3. And these values are equal. So our limit at that point equals just the function evaluated at the point. So we can say this one is actually continuous. Now, one quick note on this graph before I erase it. We said initially this is discontinuous, right? Because it has a bunch of discontinuities in it. But at the same time, we did find it's continuous at a point. So all it takes is one point to make the function discontinuous. And of course, we can evaluate at a point like we just did over here for these 4 examples. But you also can evaluate the continuity on an interval. So like, let's say we wanted to look from like 3.5 to infinity. Well, it appears that this is continuous here. Like we could look at any point. I mean, you can't look at any point to infinity, but looking at points greater than 3.5, the graph appears to be continuous. And then you could do the same thing in here, like on a different interval, like let's say from -0.5 to +0.5. So on the interval from -0.5 to 0.5, just by going by the graph visually, it appears that the function is continuous in that interval. Okay, one last thing I want to look at before we finish this up. We have here on the board the graph of our f of x, which is just x cubed plus 2. Now, whenever we found the limit of this, there's not really too much to it, right? Because we've got a curve here with no breaks in it, no problems, we're not dividing by 0. There's nothing really to think about. So what we've done in the past is we want to evaluate the limit as x is approaching 2. Now, if we just look at what happens, what is f of 2? Well, f of 2 is 2 cubed plus 2, that's just 10. So what we've always done with this is we just said, well, there's no problems here, there's nothing going on here, there's no divide by 0, so why can't I just plug in 2? And then we say our limit's 10. And actually that's fine, there's nothing really wrong with that, but the only thing is, the reason we're able to do that is because this curve is continuous, and we haven't said that previously, is when the curve is continuous, because we have our definition, because that's actually what this definition is saying, is if this is continuous, then our limit at our a point, which is 2, is going to be just the function at that point, our f of 2, which is 10. But the only problem here is that we have some circular reasoning going on, because when we calculate this limit, the way we do it is saying it's continuous, but in order to prove that it's continuous, we have to find the limit. So it's just kind of going around and around in circles. So this is actually why we have the formal definition of the limit, or the delta epsilon definition of the limit. So that actually allows us to prove this without going in circles where the continuity depends on the limit and the limit depends on the continuity. So hopefully that made sense and hopefully it helps. So we'll stop it there. Thanks so much for watching. Have a good day.